In this lesson, we're going to begin our study of differential calculus by looking at the concept of a rate of change, and we'll focus this time on what we call average rates of change and something associated with those called secant lines. Here's the plan. We'll begin by taking a look at the concept of a rate in general, and then we'll turn to how to interpret and represent rates graphically, which will allow us to use our tools for working with graphs to develop differential calculus. Let's begin by recalling the concept of a rate. Rates you can think of as measurements of change. So if you think about when something is changing, we can usually assign a kind of number that tells us how quickly the change is taking place. Sometimes the number will also indicate something about the direction of the change. We'll set that aside for now, though we'll come back to it later. That number is what we call the rate of change. And if we want to find this, one way to do it, if we're talking about a function with an independent variable and a dependent variable, is to make a change to the independent variable and then to look at how the dependent variable changes. If we look at each of those and take the ratio of them, we obtain a single number that we call the rate of change in question. So we can express this using a kind of formula. A rate of change can be thought of as a change in a function's dependent variable divided by a change in the independent variable of the function. Let's look at some examples. You're familiar with a number of these. One example is what we call the velocity of a moving object. So when we measure an object's velocity, we're interested in how its position is changing over time. So in that case, the independent and dependent variables that we use to measure the velocity are time, that's the independent variable, and position. Another similar sort of rate is what we call the acceleration of a moving object. This is similar, but not quite the same. In this case, the independent variable is still time, but the dependent variable is now velocity. And so acceleration measures how quickly an object's velocity is changing as time passes. Another example, getting away from moving objects for a second, is something like the fuel economy of a car. So in this case, the independent variable of the function we're interested in would be volume, how much fuel the car is using. The dependent variable in this case is something like position. And so the fuel economy of a car tells you, in effect, how much you can change your position or how far you can travel with a certain amount of fuel. Another fairly familiar example is something like the unit price of bananas at a grocery store. So in this case, the independent variable would be something like the weight of the bananas that you're purchasing, and the dependent variable would be the total price that you pay. And then the rate of change would give you something like the price per pound or the price per kilogram. These are all examples of different kinds of rates. Now, when we're talking about rates, it often helps to talk about units of measurement alongside them. Whenever we're talking about a rate of change, if we know what the independent and dependent variables are of the function we're studying, then the unit for the rate will be dependent units per independent units. So let's think of a version of one of the examples we just considered. Let's say we have a moving object and we're looking at its position and its time. So let's say we're measuring the object's position in meters and the object's time, or the time during which the object is moving, in seconds. In that case, the velocity, which would be the rate of change of the object's position over time, would be measured in meters per second, position units per time units. And you'll often see abbreviations like what you see here, m/s or m/s, as an abbreviation for meters per second. If we switch the rate we're talking about to say acceleration, now the dependent variable unit, if we're using the same basic units to start with, will be meters per second. Because in the case of acceleration, the dependent variable of our function is velocity. So our dependent unit is meters per second. Our independent variable, or our unit for our independent variable, is still seconds for time. And so our acceleration units would be meters per second per second. Now you might see that abbreviated with what you see there, m/s over s or something like that, although it's common to kind of simplify that algebraically and to write it as m over s squared. In other words, meters per, we say, second squared. One reason to keep all this in mind is because if you're interested in taking the AP Calculus AB exam, one thing you'll often have to do on that exam is to identify the correct units for certain rates of change. And we'll come back to this again and again as we look at the different ways in which we can use calculus to study rates of change. Let's go back now to something we looked at a while ago, the idea of an object's average velocity. So back when we first introduced limits, we had an example in which we had a falling stone, and we had a function that gave the distance that the stone traveled or had fallen, measured in feet now, so that's what we're calling y. And this equation, y equals 16t squared, defines y as a function of time t, and we'll say that we're measuring time in seconds. And so one thing we were able to do with this equation is to find the stone's average velocity during the first 2 seconds of its fall, starting at time 0 and going to time 2. We did this by using this formula for the average velocity of a moving object, change in position over change in time. In this case, our change in time is 2, or 2 minus 0, since we're going from time 0 to time 2. And our change in position can be found by finding the value of y for those 2 values of t, and then subtracting. And we calculated that that gives us 32 feet per second. So that was the average velocity of the stone over those first 2 seconds of its fall. Let's generalize this a little bit. We can do the same kind of thing to talk about the average velocity, or more generally, the average rate of change of any function. So let's say we have a function f, and it has an independent variable we'll call x, a dependent variable we'll call y. So y is always equal to f of x for some value of x. Here's a formula that will give us the average rate of change of our function from, say, x1 to x2, where x1 and x2 are any 2 values of x. It looks like this right here. F of x2 minus f of x1 over x2 minus x1. This is just the formula we used earlier for average velocity, but generalized to apply to any function that can measure anything at all, not just position and things like that. Or if we want to write this slightly differently, rather than using function notation in the numerator, f of x2 and f of x1, since f of x is always equal to y for some value of y, we can say that this is equal to y2 minus y1 over x2 minus x1, where y2 is f of x2 and y1 is f of x1. And that gives us a formula for the function's average rate of change from x1 to x2. Now, the second expression you see there, y2 minus y1 over x2 minus x1, probably looks familiar. You might have seen that and said, oh, wait, I've seen that before. It's how we calculate a slope of a line. And that then leads to a kind of graphical interpretation of a function's average rate of change over some x interval from x1 to x2. So let's take a look at that graphical way of interpreting this idea. Let's go back to the average velocity of the stone example. So we're going to look at the graph of the function that gives us the stone's distance traveled at various times. There's the graph. It's a parabola. We're only looking here at the right half of it because we're assuming that time starts at time 0. But there's the parabola there. And you can see plotted there the points 0, 0 and 2, 64. So by knowing that those 2 ordered pairs are on the graph, we know that at time 0, the stone has fallen 0 feet. And at time 2, the stone has fallen 64 feet. Now, I'm going to draw a line, a straight line, showing up as a dashed red line here, going between those 2 points. If you have 2 points in a coordinate plane, you can always draw a straight line connecting them, and that's what we have here. The slope of that line is the average velocity that we found earlier, 32 feet per second. If you go back and look at the calculation we did to find the stone's average velocity over those 2 seconds, you'll see we did the same calculation that we would use to find the slope of that line, y2 minus y1 over, in this case, t2 minus t1. So that the slope of that line is the average velocity of our function over that x interval. Here's the calculation once more, right? If we're interested in finding the slope, we're using the slope formula, m equals y2 minus y1 over x2 minus x1, and that gives us 32. Again, the same thing we got for the average velocity earlier. This leads us to something called a secant line. So that straight line that we drew between 2 points on the graph of our function, the graph which was not a straight line, by the way, is called a secant line for the function. In this case, it's our distance function for the stone. And again, we can generalize this to talk about any function. If we have a function defined by an equation y equals f of x, and we have the graph of the function, we can draw the secant line of the function from a to b. It'll be the line going between the points you see there, a f of a and b f of b. And those 2 points are guaranteed to be on the graph of the function. By the way, the word secant here and secant line might make you think of the secant function in trigonometry. There's no important connection with that, although if you go way back to when people first started studying trigonometry, the names are related, but not in a way we need to worry about. So you don't need to worry about remembering all the details of the trigonometric secant function right now. Let's look at an example. We're going to find an equation for a secant line. It's a line, so we can find an equation for it. It'll be the secant line of the function defined by this equation, f of x equals x cubed minus 3x. And we'll say that we want the line going from x equals 1 to x equals 2. Now, since we're trying to find an equation of a line, we need 2 pieces of information. We need a point and we need the slope. Well, we can find the points easily enough. In fact, we can find 2 points. We only really need 1 for a point, although we'll need 2 for a slope. But there are 2 points on the line. One of them is going to be where x equals 1. The other is where x equals 2. And the y coordinates will be the function values at those x values. So we just need to find what f of 1 and f of 2 are. F of 1 is going to be 1 cubed minus 3 times 1. And that puts us at the point 1, negative 2. We do the same thing with our other point, 2f of 2. We'll plug 2 into our function expression, and we get that this comes out to be the point 2, 2. So these are 2 points on the graph of our function, and they're the 2 points that our line is going to go through in order to be a secant line of that graph. Now that we have the ordered pairs of 2 points on the line, we can find the slope. We do this using the slope formula like usual. There's what we get if we plug in our x and y values from our ordered pairs, and that works out to be 4. So our secant line has a slope of 4. We can then write an equation for our line in point slope form. I'm just going to use the second point we found, the point 2, 2. We know the slope is 4, and so we get this equation for our line. Y minus 2 equals 4 times x minus 2. There are other equations we could write for the same line, but this one does the job. So there we go. That is an equation for the secant line of our function from where x equals 1 to where x equals 2. Real quick, I mentioned something about the point slope form of a linear equation a moment ago. The equation we wrote for our line was in point slope form, which is usually written like this: y minus y1 equals m times x minus x1, where m here, as usual, is the slope of the line in question, and x1 and y1 are coordinates of a point on the line. Any point will do the job. We're going to be using point slope form in calculus quite frequently. And that's because it allows us to use any point on the line in question. You might be more familiar with a different linear equation form, slope-intercept form, often written as y equals mx plus b. The problem with using slope-intercept form all over the place in calculus is that we will very rarely know a line's y-intercept. Now, often we would be able to find it, but that would be extra work that we don't need to do and that we might make a mistake in. So, especially since the AP Calculus AB exam does not require linear equations to be in any particular form, we're going to use the most efficient one available to us. We're going to stick with point slope form most of the time when talking about equations of lines in this course. So I suggest memorizing the form, getting the habit of using it, and trying to put your linear equations in that form in order to get practice producing equations of that form. Getting back to our main discussion point here, let's define an average rate of change of a function graphically. And to do this, we'll use the concept of a secant line. We will say that a function's average rate of change from where x equals a to where x equals b is the slope of the secant line from where x equals a to where x equals b. So if you know how to calculate the slope of a line, then you know how to find a function's average rate of change. It's the same calculation. There's the formula or the expression that we use to do this, f of b minus f of a over b minus a. That will give us the function f's average rate of change from where x equals a to where x equals b. Let's take a look at another example. We'll find the average rate of change of this function here, the sine function, from where x equals pi over 4 to where x equals pi over 2. So to do this, we need to calculate the slope of a line, the secant line of the sine graph, between those values of x. And here's the expression that will do that for us. F of pi over 2 minus f of pi over 4 over pi over 2 minus pi over 4. So using what we know about our function f, we can replace those function expressions in the numerator with corresponding sine function values. And in the denominator, pi over 2 minus pi over 4 is pi over 4. There are the values of the sine of pi over 2 and the sine of pi over 4. And with a little bit of algebraic work, we can get an expression for our secant line slope or for our average rate of change. 4 minus 2 times the square root of 2 over pi.